Hi, my name is Mariana Robles, and this is my lab report for Lab 2 on projectile motion. Here's the table of contents for the presentation. Firstly, the introduction. The overall purpose of this assignment is to observe, analyze, and model the motion of a projectile. We will be using three main tools for this: the tracker for the video analysis, GlowScript for building the computational models and only accounting for gravity and the other accounting gravity and drag force, and spreadsheets for comparing the observed trajectory of the object from video analysis with two predicted trajectories from the computational models. All this will help us gain a deeper understanding of the bigger picture behind Newton's second law of motion and the effect of drag force. So here we have Newton's second law, and then the momentum update formula, which then we can derive the velocity update and the position update formula. The velocity update and position update are very important for this experiment because that's what we use to edit in the GlowScript code so we could get the actual um, data points that we were using in the tracker video. Uh, The momentum principle states that the net force acting on an object is equal to the rate of change of its momentum over time. In other words, when a force is applied to an object, it changes its momentum, which is the product of its mass and velocity. We can see here by deriving from the momentum principle, we can obtain the velocity update. This formula allows us to determine the opposite object's velocity at each time step when dealing with a non-constant force. For the video lab, here we have recorded a video of a crumpled piece of paper falling, um, being thrown out of a person's hand. And then we recorded it and plotted each point in order to get the curvature of the projectile. For the glow strip code with data we collected, we were able to construct a computational model of the motion we observed. It is important to note that the mass of the object had no influence here, given that what we previously concluded from the equations. Um, for the B, we use zero to account only for gravity. Then we reanalyze the trajectory using a drag force similar to our experiments data. For here, we put the not only the x component but the y component since it is a two-dimensional projectile, and then B0 for no drag force. And then down here, we have the velocity update and position update. Then for the drag force script code, um, we changed the drag force, we changed to 0.015 to account for this second scenario. And then for the net forces, we put that we had to account for not only gravity and drag force, and then F net would be these two summed up. Then for the final graph, as we can see here, the orange dot represents the computational model results only accounting for gravity, the green accounting both gravity and air resistance, the blue dots representing the video analysis position. So you can see the blue dots take a curvature, which represents the real world environmental factors that we're affecting the crumbled up paper. The orange data is slightly lower than the tracker video because it is only taking into account gravity. Then the green dots are meant to represent the lowest model of the observed trajectory of the ball as it accounts for both drag and gravity. Like the observed result, it also takes a curvature. Cabrón. Me asustaste. Brother, yo... Puñeta, ¿cómo cortó ese puto video? Ay, whatever. Now, to reflect on the overall experiment, we can answer these questions. Do any of the models predict terminal velocity? Yes. The data with drag, aka the green dots, is a model that should predict terminal velocity as though it is leveling off in the end more so than the other points. What if the other objects were thrown initially up with the same initial speed? If this were the case, the total time it takes for the object to reach the ground would be longer than the original drop time because of the extra time needed for the object to reach its peak. Thank you.